Alrighty, let's see. Making sure that audio is working, and it looks like it is. Perfect. Let us go ahead and get started. Okay, so today's lesson is on Unit 9, and we're on 9.3. Okay, this is on Wednesday and Thursday. And of course, this is kind of our weird day where we have review, then we take a quiz, and then we take 9.3. Um, but luckily, 9.3 is short enough and, in my opinion, easy enough to be able to do all of that at the same time. Okay, but let's go ahead and talk about this work here. Okay, the first thing I want to kind of add here is we look at key point 4, and key point 4 is nothing new. Okay, it's definitely something we've seen before. Maybe the minor arc and major arc differentiation is a little bit new as far as like a chord is concerned, but for the most part, we should already kind of make that association. Okay, but something that isn't quite as new is or rather, what is new is 10.6, 10.7, and 10.8. 10.6 basically says if chords are congruent, then arcs are congruent, but it's also true the other way around too. So if arcs are congruent, then chords are going to be congruent as well. Okay, so it'll work both ways. And then for 10.7, 10.7 basically just tells us this. If diameter is perpendicular with the chord, then chord is bisected and arcs are congruent. Okay, so that's what we should have here. 10.8, it really is just the converse of 10.7. So they're very similar. I don't think there's a huge need for it, but it basically just tells us that QS is the diameter if we have a perpendicular bisector. Okay, so useful, yes. Entirely new, not necessarily. Okay. Then we have example 5 and extra example 5. Here, this is what I mean by it gets like really easy. Okay. And in actuality, 9.3 is only 4 slides, and we're already now on the second slide. So we're already almost halfway there. In the diagram, circle P is congruent to circle Q. Segment FG is congruent to segment JK, and the measure of arc JK is equal to 80 degrees. Find the measure of FG, or the arc of FG. Okay, there's a couple things here, right? Since the circles are congruent, the circles are congruent, we know that much. And we know that the chords are congruent. Then we can say that the arcs are congruent. Okay, that's what we're able to say from this. We're basically blending 10.6, what we just learned, and 10.3 back in the previous lesson. And what this allows us to say is that, well, we know that if these circles are essentially the same circle, which they are, they're congruent to each other, and I know that the two chords are the exact same, which in case you were a little confused as to where these chords are coming from, or why am I saying these chords, F, G, and J, K are our chords right there. Okay, we know that these two are congruent. Because they're congruent, using that 10.6 here to our advantage here, we know the arcs must be congruent. So you could simplify with words, right? Since FG is congruent to JK, then arc JK is congruent. Actually, I'm going to write that a little bit backwards. Sorry. FG is congruent to JK. The arcs are, at least. Okay. And so if I already know that FG, or rather JK is equal to 80, then I know that FG is also equal to 80. So this is actually much easier than we think it's going to be. And you'll follow the exact same logic, for example, extra example 5. You don't even need the time to do the work on your own. Because we've already done a lot of the back work and basically kind of planning here, the framework is there, we know automatically that FG is going to be 120 degrees because JK is 120 degrees. Okay, but notice it is the exact same thing, just with a different number. Okay. Not too difficult, not too difficult. However, we can have some algebra involved here. Okay. And this example 6 here is going to really incorporate 10.7. Okay. Going to really incorporate 10.7. Here, we want to find HK. HK is this blue line there that I've marked. Then we want to find the arc of HK, which is this red curve here. Not quite a semicircle. We're not crossing that middle point there. But since I'm already in red, let's go ahead and find that arc. And here we have JL is diameter. Segment JL is diameter. And we also see that HK is a chord. And according to our 10.7 theorem, if the the diameter and the chord were to cross each other and be perpendicular, then that means that their segments, the chord segments, are going to be congruent or bisected, and that means that the arcs are going to be congruent. So if that's the case, then we're going to use that. HK is a chord, right? Which therefore means that these two arcs must be the exact same. So we'll write JH arc, or arc JH, and arc JK are going to be congruent to each other or equal to each other, however we put it. Since we already know these are definitive values, 11x equals 70 plus x, we'll just solve. $70. And then we get x equals 7. Of course, that is not our answer. We're not quite done yet. We'll plug it right back in. Let's say we plug right back into JH. I suppose this would be technically the measure. Right over here, it would technically be the measure. The measure of JH is going to be 11 times 7, which of course that's going to be 77. But be careful here. This is not what we want. We wanted HK, which is the whole arc. But realize that if I know that that one piece, half of my arc is 77, then that means the other half of my arc has to be 77 as well. Just multiply it times 2. We should get 154 degrees as the measure of HK, or the arc of HK, I should say. That's pretty easy. But finding HK is going to be even easier because we know that the chord segments are bisected. They are split in half. That means NK equals HM. NK equals 7. Means HM equals 7. And because we want to find HK, the entire segment, using that segment addition postulate, 7 plus 7, or 7 times 2, whichever one you prefer, equals our HK, which means that HK equals 14. That's it. Go ahead and try this next example on your own. come back. First, you gotta find KH. KH is this chord right there. And just because I don't want to have to do all the work again, which really, is probably a good thing, but we've already can explain why we are able to do some of these things. Why I'm able to say that HN is equal to 14. All right, we just talked about beforehand. We know HN to be equal to 14, and we know that we had to get HN plus NK to equal HK, which is just 14 plus 14, which equals 28 HK. Pretty self-explanatory, I think. But then we have to find the arc of HLK. And you want to be careful here. This is a little bit different from the last problem. So here we start at H, and we had to follow the order. So H directly to L, directly to K. And that's what I want. I don't want the congruent arcs. Okay, but I am going to use the congruent arcs to figure out what the HLK arc is. So how are we going to do that? We're going to do the exact same thing we've done before. Put them equal to each other. We're going to get x's on the left-hand side. All the other numbers to the right-hand side. We get 3x equals 135. Divide 3 on both sides. X equals 45. Good so far. We'll just go ahead and plug in 45 for our 2x. 2x, or 2 times 45, minus 8. You get 90 minus 8, which is 92. Or not 92, 82. Okay, 82. But of course, we know the other arc is also going to equal 82, so multiply by 2. And that's going to give us our 164. And because we don't want the 164, we're going to take 360 and subtract from it. That's going to give us our answer of 196 degrees for the measure of HLK, this major arc. Okay. Pretty simple here. Pretty good. And the last thing we're going to cover is this theorem, 10.9. What we call equidistant chords. Okay. If two chords are equidistant from the center, that means that they are congruent to each other. In layman's terms or in easy terms, basically, we know chords congruent if the same distance from center. And one quick thing I would add here as well, when we talk about distance, we really mean shortest distance. Okay, so just kind of remember that we do mean shortest distance when we say that. Okay. But then it's also true the other way around too. So if same distance from center, chords are congruent. Okay, they both kind of work the same way. And so we have this extra example 7. I'm skipping example 7. I don't think it's a very good example. It's just, I don't think it's very good in my opinion. But we'll go ahead and look at this. Q is the center of the circle. Okay, very nice. We also know that CD equals AB, which equals 24. So I'm going to go ahead and highlight that. So this and this. I'm going to put 24 there. 24 there. Then it also tells me that I have a QM, which is x plus 3, which is this part right here. Then it also tells me I have a Q in, which is 2x plus 1. And we're tasked to find the radius of the circle Q. Okay, there's a couple ways you can go about this first. Okay. But I think the easiest way, at least in my opinion, the easiest way that is going to be helpful here is, well, we just go ahead and solve for that Qn and Qm, right? We're using theorem 10.9 to our advantage here, so we know we have to do it at some point. So let's go ahead and do it. We get 2x plus 1 equals x plus 3. Subtract the x, subtract the x, subtract 1, x equals 2. Plug 2 back in, you get 2 plus 3 equals 5. And then, of course, it should be the exact same, which it is. 2 times 2 equals 4, plus 1 is 5. Very good. And so essentially, we're saying that 2x plus 1 is equal to 5. Okay. But that still doesn't really help us figure out our radius, at least not from what we can tell from right here. Okay. And this is where it gets a little bit tricky, right? I think the intuition is there. I'm not necessarily agreeing with it per se, but something that we could know is that Cn, this segment, is congruent with ND, the same that AM and MB are congruent. And there's a reason for this, right? These are going to be bisected segments. What that means for us is that if we know we are already 25, or sorry, 24, then these segments are each 12. Okay. And then the last piece to this, the very, very last piece, I'm trying to figure out what color I want to use now. Use this one. The very last piece here is to figure out what our radius is. But remember, the radius definition means to have a endpoint on the center of the circle and to have an endpoint on the actual circle itself. So by technicality, if I take this C point and I were to, oh, I don't know, mosey on over here to the middle, that is what we call our R, our radius. Because we call that our R, our radius, let's go ahead and draw the shape that is created. Would you look at that? We have a right triangle with the radius being the hypotenuse. Isn't that just crazy? And so because we know this, right, we're trying to solve for R. The only way that we can solve for R for a triangle, or specifically a right triangle, is using Pythagorean theorem, everybody's favorite. So 12 squared plus 5 squared, because these are our two legs, equals R squared. 12 squared is 144, 5 squared is 25, equals R squared. We get 169 equals R squared. R is going to equal 13. And that is all of 9.3. So I hope you enjoyed it. Very quick, short lesson. But we'll go ahead and wrap up for the day. Just making sure that everything's still recorded nicely, and I think it did. But otherwise, I will let y'all go. I'll see y'all some other time, and talk to you later.